Hello, this video will cover content relating to subatomic particles and other properties of the atom that are in line with the content associated with the standard introductory high school chemistry course. In this video, we will be analyzing the history of the atom, the subatomic particles, isotopes, and electron configuration. These are the various models of an atom and how it has evolved throughout time. The first model was the Dalton model that came to the conclusion that an atom is a hard, dense sphere. Subsequently, we came to thought that according to the Thomson-Plum-Pudding model, that an atom is a positively charged sphere with negative charges dispersed throughout it. This led to the discovery of electrons via the cathode ray tubes experiment. Later, according to the Rutherford model, we came to the conclusion that atoms are mostly empty space with a small, dense positive nucleus, and this was observed using the gold foil experiment, which will be discussed further later. The next model was the Bower planetary model, which stated that atoms have electrons in specific orbits around the nucleus. The next and most recent model of an atom is the wave mechanical model, which defines an atom to have electrons that are confined in three-dimensional areas of space called orbitals that surround the atom's nuclei. Thomson's experiment using cathode rays came to the conclusion that subatomic particles called electrons existed by analyzing the relationship between the negative poles of the atom, which came to be the electrons, with the cathode rays and the subsequent electrostatic repulsions that came from that. The Rutherford model, which is in basis of the gold foil experiment, consisted of alpha particles, which are positive helium nuclei that were accelerated towards a thin gold sheet. The majority of the alpha particles that were fired into the gold sheet passed through. However, some particles were deflected. The fact that a very small percentage of particles were deflected led to the conclusion that the majority of an atom is empty space, where the part of an atom in which the particles were deflected is not empty space. And since that was a very small region, as most of the particles passed through, that was indicative that most of the volume of an atom was empty space. These are some assessment questions on the history of the atom. Question 1. Which statement describes the earliest model of the atom? The best fitted choice would be A. An atom is an invisible hard sphere. As it is to our understanding, this isn't necessarily true anymore. However, the question is not asking for which choice is necessarily correct. It is asking for the statement that describes the earliest model of the atom, and that would be A. Question 2. The best chronological arrangement of the given events would be D, as we have established in question 1. Event B, being that atoms are hard, invisible spheres, were the first conclusion to be made. So B is the first one. And subsequently, event A occurred, in which we discovered electron shells outside of a central nucleus, And then, via the gold foil experiment, we came to the conclusion that C was true, in which most of the atom was empty space. So thus, the answer for question 2 is D. Question 3. 4 statements about the development of the atomic model are shown below. The answer to this question, the question is asking which order of statements represents the historical development of the atomic model. As we know, the D came first, as we first came to the conclusion that atoms are hard, invisible spheres. So that leaves us with choices C and D. And the gold foil experiment that came to the conclusion that atoms were mostly empty space with a small dense nucleus, or statement C, came chronologically last, meaning C has to be our answer. Question 4. The results of the gold foil experiment led to the conclusion that an atom is, as we have already established, the gold foil experiment in fact of that the majority of alpha particles penetrated straight through the gold foil was indicative that the majority of the atom was empty space with a small and positively charged nuclei. So the best fitted choice is B for question 4. Question 5. The gold foil experiment led to the conclusion that each atom in the foil was composed mostly of empty space because most alpha particles directed at the foil, the answer is A, passed through the foil. Question 6. In the late 1800s, experiments using cathode ray tubes, or Thomson's discovery, led to the discovery of the answer is A, the electron. Chapter 2, Subatomic Particles. The three main subatomic particles in an atom are the protons, which have a positive charge of 1, a mass of 1 atomic mass unit, and are located in the atom's nucleus, along with neutrons, which have no charge, also a atomic mass of 1 atomic mass unit, and like protons are located in the atom's nucleus. And electrons, which have a negative charge of -1, and it is important to note that electrons and protons have the same magnitude of charge. The only distinction that is that protons' charge is positive, +1, where electrons' charge is negative, or -1. Electrons have very close to zero mass, where it can be assumed that they have a mass of 0 AMU, and electrons are located outside of the atom's nucleus in principal energy levels. Here is an illustration of what we just discussed. Protons are positive, the red particle illustrated here. Electrons are negative, and electrons are located outside of the atom's nuclei, whereas protons and neutrons are located within the atom's nucleus. Protons are illustrated by the white particle because protons do not have any charge, thus there is no positive or negative sign associated with it. The number of protons is what would be referred to as the atomic number of an element. Each element has a specific number of protons, and the number of protons in that element is indicative of what element it is. The number of protons in the nucleus of a specific element's atom is its atomic number. We've already discussed this. So in this depiction of a carbon atom, we see the atomic number, the number in bold is 6. This is indicative of the fact that carbon has 6 protons. Here is some independent practice to try on your own. I will suggest pausing the video so that you can conduct the problems here by yourself and then resume the video to check your answers. Okay, I'm assuming you've already tried these on your own. If an atom has 17 protons, we can conclude that its atomic number is 17. If you have a periodic table of elements on your person, you can look this up and see that the element that has an atomic number of 17 is chlorine, which has an elemental symbol of Cl. Cobalt, which has an elemental symbol of Co, has an atomic number of 27. Thus, we can conclude that cobalt has 27 protons. The element with 5 protons, which has an atomic number of 5, is boron, with an elemental symbol of B. The number of protons in a tungsten atom would be 74, because the atomic number of tungsten is 74. The element of an atom that has 87 protons would be franium, or elemental symbol Fr, because the atomic number of franium is 87. In a neutral atom, the number of protons must equal the number of electrons. As we have established, protons and electrons have the same magnitude of charge, but protons have a positive charge, where electrons have a negative charge. Thus, in order for an atom to be electrostatically neutral, the number of protons must equal the number of electrons in order for the positive and negative components of the atom's charge to cancel out. Looking at this diagram, since we see 2 protons in the atom's nuclei, we can conclude that the atomic number of the atom is 2. The element with atomic number 2, based on the periodic table, is helium. Thus, the element that corresponds to this image is helium. The mass of an atom comes from its nucleus. Since electrons do not have a mass, the mass number of an atom can be mathematically set equivalent to the sum of the number of protons and neutrons in that atom. In this illustration, we can see that this atom has 2 protons and 2 neutrons. Thus, we can conclude the mass number of this atom is 4, since the sum of the number of protons and neutrons, in this case 2 plus 2, is 4. Here is some independent practice you can try on your own. Here are some assessment questions that align with the content you will be assessed in the New York State Regents curriculum, along with any other high school chemistry course. Question 1, the mass of an electron is equal to the mass of an electron is less than the mass of a neutron. Thus the answer is D. Since, as we know, the mass of an electron is essentially 0 AMU, whereas the mass of both protons and neutrons is 1 AMU. Thus, the mass of an electron must be less than the mass of both a proton and neutron. Thus the answer is D. Question 2. In all atoms of bismuth, the number of electrons must equal the... Now, I would like to note that this question is not assessing you specifically on bismuth. This question the answer choices in this question applies to all atoms. So the number of electrons must equal the number of protons. So the answer is A. When an atom is in its elemental form, it must be electrostatically neutral. Thus, the number of protons and electrons must be equal to one another. The answer to question 2 is A. Question 3. Which particles are found in the nucleus of an argon atom? The particles found in the nucleus of all atoms are protons and neutrons. Thus the answer is C for question 3. Question 4. The atoms are neutral because the number of protons must equal the number of electrons. The answer to question 4 is B. Question 5. The mass of a proton is approximately equal to the mass of. The answer is B, a neutron. As we have established, the mass of both a proton and a neutron is 1 AMU. Which phrase describes an atom of aluminum? The nucleus of all atoms are positive, and all atoms are surrounded by negatively charged electrons. Thus, the answer to question 6 is C. Question 7. Which statement describes the charge of an electron and the charge of a proton? An electron has a charge of -1, and a proton has a charge of +1. Thus, the answer is D for question 7. Chapter 3. Isotopes. If we look at this illustration, we notice all of these atoms are indicative of the element carbon because all of these atoms have 6 protons. However, we do note that each atom has a different number of neutrons. All of the atoms of carbon that we've just observed are all isotopes of each other. Based on this rubric, we can define an isotope as two atoms that have the same number of protons but a different number of neutrons. And subsequently, as we know, neutrons have an atomic mass of 1 AMU. So if the number of neutrons differs between two atoms, the mass or the mass numbers of each of those atoms will be distinct of one another. One way we can express the notation of an isotope is through this method. X denotes the elemental symbol, A denotes the atomic number or the number of protons plus neutrons, and Z denotes the atomic number, the number of protons. A way of remembering this is that the number on top, in this case represented by A, will always be greater than the number on bottom, or in this case Z, because the sum of the protons and neutrons must be greater than just the number of protons. Isotopes can also be represented using the name of the element followed by the mass number of it. So in this case, this is an isotope of carbon because normally carbon in its elemental form has 6 neutrons. However, in this case, there are 7 neutrons. So thus we can express this isotope of carbon by noting it as carbon-13. The name of the atom, which is carbon, followed by the mass number of the atom, in this case 13. Both of these ways are both valid in expressing the isotope notation of an atom. Here is some practice you can try on your own. Here are some assessment problems on these topics. Two atoms that are different isotopes of the same element all atoms of the same element have the same number of neutrons, but if they are distinct isotopes of one another, then they must have different number of neutrons. Thus the answer is B for question 1. Question 2. Which notation represents atoms that have the same number of protons but a different number of neutrons? So if the number of protons are the same, the element must be the same. So this rules out choice A and D. Now, if it's an isotope, a distinct isotope of one another, then the number of protons are different. So since sulfur 32 and sulfur 32 both have the same mass number, that means they have the same number of neutrons. This question is asking for a different number of neutrons. Thus the answer is C, because chlorine 35 and chlorine 37 both have different mass numbers and thus different amount of neutrons. Question 3. Which two atoms represent isotopes of the same element? Now, if they are the same element, the number of protons are the same. So by this rubric, we can tell that the answer must be C, atom D and E, because the number of protons are the same, but the number of neutrons are different, and this is the definition of an isotope. Question 4. Chlorine 37 can be represented by? The answer is D, because the element on top in this type of isotope notation is the mass number, which must be greater than the atomic number, which is the number below it. Average atomic mass. The mass number of an isotope is representative of the average atomic mass of all naturally occurring isotopes of that atom. An analogy you can develop between average atomic mass and something you may be more familiar with is grade point average. In your class, assessments, homeworks, and labs may all have different weights. However, if you were to compute the weighted average for that class, you would have to consider the weight that each assignment has, as an assessment will have a greater weight on your average than a lab, which will have a greater weight on your average than a homework. Now, if we were to apply this analogy to average atomic mass, we can use this formula, which essentially states that the mass of an isotope, of an atom, I should say, of an isotope of an atom, I should say, multiplied by the percent abundance of that isotope divided by 100 plus the same process for all isotopes of that atom equals the average atomic mass of that element. If we were to do this process for isotopes A and B, we can express this mathematically as 6 multiplied by 7.5 divided by 100 plus 7 multiplied by 92.5 divided by 100. If we were to do this computation, the answer would be 6.925, which means the average atomic mass is 6.925. This makes sense as the percent abundance of isotope B with mass 7 is significantly more common than the percent abundance of isotope A. Subsequently, you would expect the average atomic mass to be closer to 7 than to 6. Thus, our answer of 6.925, which is clearly closer to 7, fits this context. We can apply this same principle in calculating the average atomic mass of an element with this example of the different isotopes of silicon. Now, if we were to express this using an arithmetic expression, we can do this by taking the product of 27.98 and 0.9222 plus 28.98 times 0.0469 plus 29.97 times 0.0309. If you were to do this computation, you would get 28.088 as the average atomic mass of this element. An important thing to note is that when doing this expression, you have to divide the percent abundance of each isotope by 100, and be sure to, when doing this math, that the atomic mass is multiplied by its corresponding percent natural abundance, divided by 100, of course. Question 5. Which numerical setup can be used to calculate the atomic mass of the element bromine based on the isotopes shown? So we have bromine 79 and bromine 81. So if we were to multiply the atomic mass and its corresponding natural abundance over 100 and take the sum of that value for both isotopes of bromine, that would be the average atomic mass for it. So looking at our options, the answers must be either C or D, because in choices A and B, they fail to divide the percent by 100. So the answers are either C or D. Now here, the natural abundance must correspond to that atomic mass. So here, 78.92 is multiplied by 0.5069. That makes sense, since those numbers correspond to one another. So the answer is C. In choice D, they multiply 78.92 with 0.4931. This percent abundance does not correspond with bromine 79. It corresponds with bromine 81. Thus the answer is C for question 5. Question 6. Which numerical setup can be used to calculate the atomic mass of Ga? The answer it would be A. As in A, they correctly divide the percent for each isotope by 100, and the percent abundance corresponds to the atomic mass of that isotope. So the answer for question 6 is A. Chapter 4, Electron Configuration. The most probable location of an electron is an orbital. An orbital essentially is a statistical distribution of the most likely regions in which an electron will be placed. As something to consider is that electrons are in constant motion, so they are not necessarily in the same location as a function of time. However, there is a statistical distribution where we can predict electrons will be, and this is represented using orbital notation. Orbitals are always located on the outside of the nucleus of an atom in principal energy levels. All atoms have 7 total principal energy levels, though that's not necessarily the number of occupied principal energy levels. Not all PELs are occupied in an atom. Electron configuration tells us how many electrons exist